We're going to take a look at direct proportion and what it means and how it's related to all of the linear graphs and the gradient that we've been studying. So just a quick definition, if two variables are in direct proportion, then the rate of change of one variable with respect to the other is constant. So that's a bit of a mouthful. We'll just take a look with an example at what that means. So something that I always think about in terms of direct proportion, having just moved to Australia from England, is the exchange rate between the pound and the dollar. So I'm always thinking, okay, if it costs this much in dollars, how much is that really in pounds? Okay, so I put the exchange rate up there for you. At the moment, for £1, you get about $1.60 Australian. So you probably understand that if you have £2, then you get $3.20, right? Because if I have double the amount of pounds, I'm going to get double the amount of dollars. If I have £3, I'm going to then get how many dollars? Well, I'm going to get 3 times $1.60, which is $4.80. What if I had £10? What would happen? Well, then I'd get 10 times the amount, so I'd get $16, and so on. I'm sure you get it. If I have no pounds, okay, then I get no dollars, right? So this is something that's in direct proportion. So there's two sort of rules. The first is that if one of the variables is 0, the other also has to be 0. The second is that if one doubles or triples or halves or whatever, the other does the same, okay? So whenever you buy things or you exchange money, those things are going to be in direct proportion. There's quite a few things that we'll take a look at. Okay, so we can show this on a graph. So a direct proportion will give us a linear graph. So if I were to say pounds on the x-axis and dollars on the y-axis, so I'll just label them here. These are my Australian dollars, and these are my, we'd say GBP, Great British Pounds. Okay, so again, if I have £0, I get $0. If I have £1, I have $1.60, so it's about there. If I have £2, I get $3.20. If I have £3, then I get, what did I say, $4.80, and so on. So you can see that this is going to create a linear graph. So I'll just draw that in. Okay, so there's a graph of pounds against dollars. If I wanted to look at the gradient of this graph, let's take a look. So I know this point is the point 160 because I graphed it. So that's the point $1.60. Okay, so if I draw my little triangle here, the rise is 160 or 1.6. We'll just say 160 because we're talking about dollars, and the run is 1. Okay, $1. So the gradient of this graph is going to be the rise, which is 160 divided by 1, which is just 160. And that makes sense because that basically, the gradient tells me that for every x value, as x goes up by 1, how much does y go up by? Well, it goes up by $1.60. So if x goes up by 1 again, y goes up by $1.60, and so on. So the gradient really tells us, especially in the context, when we have a context like this, it tells us the rate of change. When I change x by 1, what happens to y? Okay, let's look at a few more examples. Okay, so like I said before, just to clarify, if two variables are in direct proportion, then we get a linear graph when we graph those two variables, and we're in the form y is equal to mx, and that's because the graph goes through the origin. So these are the things that we covered in the lesson about graphs that just go through the origin. Okay, and the gradient, like I said, is the rate of change of y with respect to x. So let's look at these two graphs, and we're going to try and determine whether or not they're in direct proportion. So this first one here, I've got time on the x-axis, and I've got distance in kilometers along the y-axis. And is this in direct proportion? Well, it is a linear graph. Okay, so that ticks off the first one, and it goes through the origin. So that is in proportion. So this is in direct proportion. Now, when I take a look at the gradient of this graph, what does it actually tell us? So this means that, let's take a look. I'll draw my little triangle. My rise is 20 and my run is 1. Okay, my rise is 20 kilometers and my run is 1 hour. So I get 20 over 1, which is just 20. And that basically tells me that for every kilometer, or sorry, for every hour I drive, I go 20 kilometers, right? So if I drive another hour, I'm assuming that we're driving here. If I drive another hour, then I go 40 kilometers and so on. So when you take the gradient of a graph that shows you time and distance, the gradient is actually equal to whatever the speed is. Okay, so that's your constant speed. So that's a really important application of direct proportion. The second graph here shows us the cost of a taxi cab. Okay, now take a look closely. Is it in direct proportion? We do have a linear graph, but this is not going through the point 0, 0. Okay, it goes through the point 0, 1. And that is because normally when you get into a taxi, even if you don't go anywhere, the cost isn't 0 right away. So in this case, even if you don't go anywhere, you still have to pay $1. So that's because the taxi rides start out with the total cost. So this one is not in direct proportion because it doesn't go through the origin. Okay, let's take a look at an example. So it says water is poured into an empty tank at a constant rate. Okay, so a constant rate implies that it's direct proportion. After 3 hours, there's 6,000 liters in the tank. What is the rate at which water is poured in the tank? Well, we pour 6,000 liters in 3 hours, so what we want the rate per hour. So if we divide 6,000 by 3, we get a rate of 2,000 liters per hour. So that's the rate at which the water is filling up in the tank. Now, can we draw a graph to show this? So always along the y-axis we're going to have, along the x-axis we're going to have time, and then what we're measuring is the volume of water in the tank. So we know that because it's in direct proportion, it's filling up at a constant rate. At 0 hours, we're not going to have any volume in the tank because we won't have started pouring it yet. And we know that after 3 hours, so we'll just go 1, 2, 3, we've got 6,000 liters in the tank. So we'll just mark here 1,000, 2,000, 3,000, 4,000, 5,000, and 6,000. So this point here is our point 3 and 6,000. Okay, because we know it goes to the origin, we can just draw a line like that. Okay, so what is the gradient of this graph? So if I were to draw in, let me just change the ink so we can see this a bit more clearly. So if I were to draw my triangle in, the rise here, it goes up to 6,000 and the run is 3. So my gradient is going to be 6,000 divided by 3. 6,000 liters divided by 3 hours. So that gives me a gradient of 2,000, and that's in liters per hour. So you can see that the gradient is the same as the rate that it was filling up. Okay, so the gradient tells us that every hour, 2,000 more liters are going in this tank. So now can we work out a rule connecting the volume and the time? And all that is that the volume is going to be equal to whatever our rate of change is, or our gradient, times whatever the time is. And you can relate that to the equation y is equal to mx. Okay, we don't have a plus c because it goes to the origin. Y is, on the y-axis, we have volume. So instead of just using the variable y, we actually give it, because it's in a context, it's a word problem, we can use v for volume. 2,000, remember, is our gradient, and x, what's on the x-axis, is time. So 2,000 times t, okay? Now we can use that rule, so that was part C, part D. We can use that rule to work out what's the volume of water after 1.5 hours. So we want to know the volume after 1.5 hours. We're going to substitute 1.5 in for T. So 2,000 times 1.5. And that gives us 3,000. So the volume after 1.5 hours is 3,000 liters. And the last bit, F, it says now use your rule to find out how long it would take to fill up the tank to 9,000 liters. So now we know V is 9,000. That's equal to 2,000 times T, which is what we wanted to find out. It says how long does it take, so we want T. So if I divide both sides by 2,000, okay, I can cancel out all those zeros. 9 divided by 2 is 4.5. So that means it's going to take 4.5 hours to fill up the tank to 9,000 liters. Okay, there's one more question which you can try on your own, otherwise you can follow along with me. So, working as a barista in a cafe, you get paid an hourly wage. 1 week you worked 25 hours and made $450 before tax. So is the relationship between hours worked and pay in direct proportion? What do you think? Is this something that's in direct proportion? Well, it is, because you get paid every hour. So if you work no hours, you get no money. But if you work 1 hour, you get a wage. If you get 2 hours, you would get double that wage, and so on. So those two things are in direct proportion. So let's draw a graph of this. So along the x-axis, we're going to have the hours that we worked, okay? And along the y-axis, we're going to get our pay, okay? So we know, first of all, that 0 hours means we get $0, and 25 hours means we get $450. Now, I'm not going to draw on the scale. I'm just going to mark in that that's the point 25 and 450, okay? Now, can we write a rule showing the relationship between the pay and the hours worked? So we want something like we did before. We want a relationship between pay and hours. So we're going to get let's just think about it as y is equal to mx. Okay, y is my pay, so I'll call that P for pay. M is the gradient of the graph, which we're going to have to work out, and x is the time that we worked, or the hours that we worked. So I'll just put h in. Now, how do we work out this here? How do we work out the gradient? Well, we need to draw a line here, first of all, which I forgot to do. So there's my graph showing how much I get. And now if I want to work out the gradient, I need rise over run. So my rise, this goes from 0 up to 450, and my run is 25. So the gradient is going to be equal to 450 divided by 25. And I'm just going to do that on my calculator, and I get that that is 18. Now what that means is, for every hour I work, I get $18. It's telling me for every value of x, so for every 1x, and x in this case is hours, I get $18. So that's my gradient, or my rate of pay. Okay, so my relationship between pay and hours is P is equal to 18 per hour. So how much would you get paid if you worked 30 hours? So now you just have to work out that. You get 18 times 30 hours. So 18 times 3 is 54, so $540. Okay, that's the end of this video. Can you write your summary and think of your question now, please?